So let's take a look at this example problem here. In this problem, they tell us that there's motion of two particles, particle A and particle B, and it's described by the following position vectors. So they give us a position vector for each of these particles. So for particle A, the position vector is given to us as 3t I, so unit vector right there, plus 9t, parentheses, 2 minus t in the j direction in units of meters. Now, if the position vector they give us for particle B is given by this expression here of 3t squared minus 2t plus 2 in the I hat direction, and plus 3 times t minus 2 in the j hat direction, still in units of meters. So that's our given information right there. What are they asking us to solve for? They want us to find the point at which the particles collide and their speeds just before the collision. So two different things that we're going to solve for on this problem here. One is a position where the particles intersect, and the second thing is their speeds just before that intersection occurs. So game plan for this one here, there's two different things we're going to think about. One, the particles will collide when their position vectors are equal. So we need to set these equal so that r sub A is equal to r sub B, and that's when they will collide. That's when they're going to intersect. Two, the other thing to think about as we're solving this is that their speeds can be determined by differentiating these position vectors. So we can start with our position vectors, set them equal to each other, do a little bit of calculus in order to differentiate these, and then from that we can get our speeds. So now that we've had a chance to read through the problem statement and understand what they gave us and what they're asking us to solve for, we now want to create our setup page here where we have all of our given information clearly labeled in one spot, what they're asking us to solve for, and then any plan of attack we have in order to go into our solution. So the first thing we want to do is write out what they gave us. So they gave us these position vectors. So we have that r sub A is equal to 3t in the I hat direction plus 9t times 2 minus t in the j hat direction m. So I've just kind of color coded these here for x and y, or I and j, for each of the position vectors. So our second position vector for particle B is 3 times t squared minus 2t plus 2 in the I hat, or the x direction there, plus a 3 times t minus 2 in the j hat direction there. Both have units of meters. Then what we want to do is figure out what they're asking us to solve for. So they want the point when they collide and the speed just before the collision. So two different things that they want us to solve for in there. And again, as we talked about before, they're going to collide when the position vectors are equal, and then we can do some calculus in order to find our speeds from that. So now that I have everything clearly labeled in a spot here, I can reference back to the next step is to begin my solution. So from our game plan here, we want to set the position vector for A equal to position vector for B. So within that, we can see we have x components and y components. We always want to separate these out and deal with these individually. So the first thing I'm going to do is take a look at just my x components. I can say that x sub A is equal to x sub B. When I get to the y components, I can see that y sub A is equal to y sub B. But let's just take a look at x, and I can say, okay, highlighted this in green, color-coded it here, so 3t is equal to 3 times t squared minus 2t plus 2. Plug that in down here. 3t is equal to 3 times t squared minus 2t plus 2. I can distribute this 3 here, move this over, reduce, and simplify, and I end up with t squared minus 3t plus 2 is equal to 0. Now there's two ways I could do this. I could FOIL this out, or I could use my quadratic here in order to solve for my value for t. So I can do it out both ways here. So I'm going to try out my quadratic here. Remember, recall that negative b plus or minus the square root of b squared minus 4ac all over 2a. It's a general form for my quadratic equation. This here, my a value for my squared term is 1. My b value from my t term here is negative 3. And my c value right here is 2. I can plug those into my quadratic equation. I end up with now t is equal to 3 plus or minus the square root of 3 squared minus 4 times 1 times 2 all over 2 times 1 there. And I end up with a value here of 2 seconds or 1 second here. So I'm going to go with this here. You can test both of them and plug them back in. So those are my values for t. And you can see if I FOILed this out up here, I have a t is equal to 1 and t is equal to 2 up there as well. So whether I FOILed or use the quadratic, I still can get a value for 2 here. So now that I've taken the time to go through and do this for my x components, I want to separately do the same exact thing for my y component. So I can reference back to my first page again and say, okay, I've color coded this. My y components here for my particle A and particle B, I have 9t times 2 minus t in the j hat, and I have 3 times t minus 2 in the j hat direction there. I can set these equal to each other there, so that's exactly what I do. Reference back, I say, okay, 9 times t times 2 minus t is equal to 3 times t minus 2. I can reduce, simplify, distribute through here, distribute 3, distribute my 9t. I end up with 18t minus 9t squared is equal to 3t minus 6. So I can go through and move things around, move 3t over this side, subtract 3t there, add 6 to both sides there. I end up with 15t minus 9t squared plus 6 is equal to 0. And simplify things more, I can see I got a common value of 3 that I can pull out front here. So I pull a 3 out front, so it's 3 times 5t minus 3t squared plus 2 is equal to 0. Divide this by both sides, reduces this down, and I have 3t squared plus 5t plus 2 is equal to 0. Move things around a little bit to get rid of the negative signs. I now have 3t squared minus 5t minus 2 is equal to 0. So again, I can do the quadratic here, where my a is 3, my b is a negative 5, and my c is a negative 2. I go back to my general form again for my quadratic equation here. T is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a there. I plug in my values there. My b is negative 5. Putting in my negative 5 there. I have my other values I can plug in here. So this is 4a. What is my a? My a is 3. C, what is my c? My c is negative 2 there. Plug this in, my 2. Again, now here times my a value of 3 there. I end up being able to plug in all my values for the quadratic. Reduce and simplify a little bit. We end up with t is equal to 5 plus or minus the square root of 25 plus 24 over 6. Or 5 plus or minus square root of 49 over 6. Reduce this down, simplify, end up with two values from this here, either 2 or a negative 1/3. So this is where I want to compare. For both my x components and my y components, I had two different possible values. Well, the one that's in common is the one that is the correct answer there. So my value for t in both of them was 2. I also had a value for 1 for my x components, and I also have a value of negative 1/3 in my y components. So 2 is the only value for time that overlaps for both of those there. So therefore, my time where these two particles intersect is 2 seconds. So with that information, knowing the time when the two particles collide or intersect, I can take that value of 2 seconds and plug it back in for t into my position vectors r sub a and r sub b for that equation there. So I plug it back into both of those position vectors there. So 3 times my value of time for 2 here. Now I had direction 9, 2 times 2 minus 2, which ends up going to 0 there. I end up with, for my position vector in the A, when I plug in a time is equal to 2 seconds, I get a value of 6 I hat. Do the same thing in the B direction here, and I end up with, okay, 3 times 2 squared minus 2 times 2 plus 2 in the I hat, plus 3 times 2 minus 2, which is 0. That goes away. I end up with 6 I hat as well there on this side here. So what I end up with looking at here, I can take a look at my individual vectors here. X sub A is equal to my initial position vector x naught is equal to 6. Y sub A is equal to y sub B is equal to 0 there. So I have my x in the I hat direction right there, 6xi. My y component is 0 there. So now I have a position for where these two intersect when time is equal to 2. So now that we know the position when the two particles collide, the next thing we want to do is find the speed just before the collision. So we have the known position right when they collide. We know the time at 2 seconds when they collide. How do we calculate the speed just before that collision occurs? Well, the way we do this is a little bit of calculus. We want to differentiate the two position vectors, A and B, in order to get our velocity vectors. So to do this, let's do these individually. Let's just look at particle A first, then we'll look at particle B. So for particle A, we can find our velocity vector by taking the first time derivative of our position vector here. So this is our given position vector, 3t in the I hat direction plus 9t times 2 minus t in the j hat. We can combine this to 18t minus 9t squared there. We say, okay, what is the derivative with respect to time of 3t? Well, that's simply 3 in our I hat direction. And what is the derivative of 18t? Well, that's 18. And what is the derivative of negative 9t squared? Well, that's negative 18t. So now I have my velocity vector here. So with this velocity vector, we can then plug in for our values of t, because we know that t is equal to 2 seconds. So when time is equal to 2 seconds, we can take this velocity vector now here, our 3I minus 18 times 2, we plug in our 2 for our t value there, plug this in, and when we do that, we end up with a velocity vector of 3I hat minus 18j hat in units of meters per second. So that is our velocity vector now for particle A when time is equal to 2 seconds. Now what we want to do is the same exact thing, but for particle B. So for particle B, again, the velocity velocity vector for particle B is equal to the first time derivative of our position vector for particle B there. Here's our position vector that we know for particle B. We have 3t squared minus 6t plus 6 in the I hat plus 3t minus 6 in the j hat direction. So we do the same thing here. We go through, we take our first time derivative. We take the first time derivative of 3t squared, simply becomes 6t. Our first time derivative of negative 6t becomes negative 6. The derivative of a constant is 0. We go over here, derivative of 3t is just 3. Derivative of negative 6 is still 0. That's a constant there. So now we have our velocity vector for particle B given by 6t minus 6 in the I hat plus 3 in the j hat in units of meters per second. Again, now we want to plug in our value for known time. Time is equal to 2 seconds here. So we can take that 2 seconds, plug in for our value of t here. So that's what we do, 6 times our time of 2, minus 6 in the I hat, plus 3 in the j hat. We end up with a velocity vector when time is equal to 2 for particle B of 6 I hat plus 3 j hat in units of meters per second. So now we can reference back the problem statement or our first page and realize that they asked us for speed. Now, speed is the magnitude of these velocity vectors. So we need to take the square root of the sum of the squares of the individual components of both particles in order to get each of their speeds. So we do that there, and we take the square root of the sum of the squares for our velocity vector of A, and what we end up with is the square root of 3 squared plus 18 squared, which is 18.2 meters per second, which is our speed of particle A just before the collision. Do the same thing for our velocity vector B. We take the square root of the sum of the squares of the individual components here. The square root of 6 squared plus 3 squared is equal to 6.71 meters per second. So that is our speed for particle B. So we have our speed for particle A and our speed for particle B. And that's the last thing that they asked us to solve for in this problem.